BreedFACE enables us phenotyping for plants under elevated CO2 concentrations at this moment. So in a lifetime of Ulo, it increased 200 ppm. But we would like to measure also what's happening 50 years later. And how to do that, I would like to introduce you. Elevated CO2, well, I don't have to talk about it anymore where it came from, but it's kind of nice to point out where we are located. Jülich, I'm from Forschungszentrum Jülich, has some other people in the room here. You see some big mines located around us. A bit more specific, we're not from the city, we're from this small remaining forest there. In that small remaining forest, there's actually a giant research institute with a lot of phenotyping activities going on. In that institute is only, again, a small bit, this red circle, with a lot of greenhouses, a bit on the dark side here, but a lot of activities going on inside these greenhouses, and also part of the EPPN 2020. Please look up the website if you want to know what's going on inside the greenhouses in relation to EPPN 2020. I would like to take a broader scale and move a little bit south from Jülich, and if you move south, you'll notice that all these fields are beautiful agricultural fields, and that's where we focus a little bit on our breed phase. Breeders improving yield, filling the yield gap for the agriculture, for the yield in the future, but under future environmental conditions. That's what's aiming for the breed phase. So we're doing that in agricultural fields in the region. Actually, we do that specifically in this agricultural field, very well managed by the University of Bonn, so-called Campus Klein-Altendorf, in the middle of a rich soil, loamy soil. So let's go a little bit more about detail. Breed phase, the field phenotyping on the elevated CO2. What is the aim there? The aim is there to look for the genetic variation that is available under the elevated CO2. This yield increases. How much did it maybe restrict the response to CO2? Or do we still have a lot of variability available there? We do this by having a non-invasive phenotyping together with elevated phase systems. It's also managed by standard agronomic practice. I'll come back to it later. I say it easily, but it's not always done in this phase sites. Typical German crop species at the moment, and that's why I'm giving this talk here. It's part of the EPPN infrastructure, so open for all of you to a certain extent to participate, to research in this infrastructure that was set up within the German plant phenotyping network, especially focusing on infrastructure setups. A little bit more about how it works. You have CO2, there's CO2, pure CO2 released against the wind direction. So depending on the wind from one of these segments in a ring of 17.5 meters, CO2 is released, and by the wind it blows over your ring here, and so these plants in the middle of the ring are constantly growing on the elevated CO2, in this case about 600 ppm. The ring itself, we have 3 of those rings that can fit about 42 plots. This is variable, of course. If you make your plot smaller, you fit more plots. But these 42 plots, this 1.5 and 3 meters, kind of the minimum what a breeder would still think that you can get a reliable yield of. So if you're not from the lines, but you're going for the testing for breeders. So this is why we have this site. It's a mobile tank for the CO2 storage and vaporize as well. And it will be equipped with to get in these rings, I mentioned already, less disturbance, a big positioning system that can drive over it. A little bit more on the mobile CO2 supply, because it's what's on one of the things that's different from all the other phase systems in the world. We made it as such, this simple drawing shows it. Our storage tanks are on chassis from trailers, and it means wherever there's electricity and in the neighborhood of a CO2 production, you can put your system up. It doesn't mean that it's so mobile, because you want to measure over a whole growing season. There is some installation to be done. At the moment, it's focused on Campus Klein-Altendorf, as I said already. In this Campus Klein-Altendorf, just to mention what I said already, it's standard economic practice. That's nice. I mean, if you mostly see these phase systems, there goes a lot of money in there. That means also a lot of people go in there. And a lot of people want to plant, I want to do this experiment, I want to do this, I want to do this. Very small, a small scale. And suddenly you start manipulating in another way your experiments and not doing the standard economic practice anymore. So what we did, we focused really also maintaining that economic practice, that you can spray over the rings and do the non-invasive phenotyping at the same time. And as well, we keep the area such that we have a large area reserved so that you can continue the crop rotation that is commonly done. So we do in the first year here, and we can measure the same crop over years if you would like to in different fields. The design of the plots of last year, we had a test year, mostly on the design, a little bit on the CO2, as I will show you later. We did that with winter wheat, and we have planted that this year again also. I will show you a picture in the end. We also tried some combining different crops, added some soybean later on, to see, just test the system, how everything is working. Picking up a little bit also on Francois' talk, environmental sensors are the basis. If you manipulate an environment, let alone you want to see how you manipulate it, that's CO2 in this case, but also the rest of the light, temperature, and all standard measured with these sensors that we have in the field, in each ring, in each control site, going directly the temperature, light, humidity data, soil humidity, soil temperature, to a database from where it can be downloaded as part of the requirements also for the EPPN 2020 field sites. The sites, the rings are equipped with are part of our field phenotyping setup. Uli showed in his introduction talk already our framework of different pillars, going from traits to environmental sensors. I didn't repeat that, but I show you an example of field phenotyping positioning systems that we have available at the moment, and that may be compatible with the phase. Whereas this is in preparation, our main focus point, especially for the breed phase. Of course, you can also fly over with your octocopters or your fixed wings. Or maybe you can put a field lift for precise measurements above it, or you go alongside with a field mobile, or just a manual practice way, drive along it with a field bike. That's still as simple, but you can test a lot of sensors in this way. Our main focus point, I would say, of our focus of our group in Jülich is where we measure a lot of traits. But if you say, what is this trait that's standing out, is photosynthesis that we like to concentrate on. And how do we measure photosynthesis from remote? It's by fluorescence. And with fluorescence, we have a whole scale of equipment sensors available where we reach from at leaf level standard palm measurements that you clamp them on leaves. You cannot get so much plots. Where we have in these mini plots is spinning containers with sensors like a lift, light-induced fluorescent transient, that can measure remote, and that makes accessible a huge scanning of plots over time and getting the same photosynthesis traits and more than the traditional palm fluorimetry. This is a passive fluorescence. The sun induces your photosynthesis, and you measure that with a spectrometer. It's a highly calibrated spectrometer, so highly calibrated it turned into a company spin-off. So if you want to buy this, one of our PhD students, some advertisement for him. If you want to go higher end, if you want to be more precise, you can measure also this passive fluorescence by more dedicated, pretty heavy spectrometers, ones that can go in planes, fly over. And this actually resulted in that, and this will not be in the image of the breed phase anymore, but that in 2021 there will be a satellite measuring fluorescence over. So then we can really track over these many years to come how the CO2 will affect large fields. But let us start in the small field, in the breed phase. Is it also easy? No, it's not always easy. Sometimes, as you see a little bit on this dramatic picture, CO2 doesn't release in all the places that you would like it to release. Well, that's why we have a test here. And that's why we are at the moment in a more sunny position where everything is going pretty smooth, where it goes from the tank through the liquid CO2 to the vaporizer and then into the field. So it's looking green and shiny. And here you see the green field of last year with the rings and with the different wheat varieties planted inside in the field of Campus Klein-Altendorf. So I must say we're pretty well prepared. What did we do last year? We did some sensor measurements as well. Not all complete, but here you see an example. I just wanted to give you two examples of sensors also that we did. Of the copters or the fixed wings that we flew over the sites. Here you see the rings with elevated CO2, and here you see the repeats of control sites. There's some spatial separation, but we checked and controlled a lot that we can get it out in our statistical analysis. So this is a time series of RGB images just taken with the drones, just as an illustration. You can see pops up some soybean in a collaborative project over time. You see also the difficulty. You cannot combine easily two crops when you want to harvest one and one is still growing. But okay, we knew that, so it was just an early figure experiment. Pick up the other one, a lift. What I said, you can measure over it. Just a small slide on what does lift do. It's a light-induced fluorescent transient method. So with a blue light in the canopy, it induces your fluorescence, and you get your photosynthetic efficiency measurements and also your relaxation rates. This relaxation rates is a new parameter giving your electron transport rate constants and capacities. that can be measured now from a distance of about 80 centimeters. Just one preliminary data slide. We repeated 3 times running over, and what we did, well, there was ambient CO2 that was alongside the ring before it, the same variety, and then the other 2s are a little bit here before because the wind was blowing over and the system was not regulating, so 2 sites with elevated CO2. And what you then see, if you, for example, look at the greenness, you see that everything is the same. So 3 times in a day we measured, well, obviously everything has the same greenness. Also, whether it is grown in or outside the ring, it also is the same greenness. Similar with your photosynthetic efficiencies, actually. But then if you look at this new parameter, one of these reoxidation rates of fluorescence, you see there's a clear effect on CO2 on these plants. You see also our handicap, we still had to drive alongside the rings to get this data, but I think it's a nice start on getting some insight on how the fluorescence changes with the elevated CO2. What's the current status at the moment? This is a picture of last week. Here you see the tubings with this laser drilled holes where the CO2 comes out. And here you see the wind control in the middle. And you see already our plants are about 10 centimeter winter wheat high. And as it is at the moment, this 42 winter wheat varieties from a historical collection. So from when Onno or agronomic actually started, got his PhD, 350 ppm. That was 1963 when the first varieties were released and were planted here again until 2013. So a mix over this whole time period to see how they respond to these elevated CO2 conditions. As I said already, it's open for EPPN projects at the trade level, also for more years to plan. If you think, I would really have this variety or this species in there, please feel free to contact me. I thank you for your attention, and of course, thank you very much for people in my group.